The what?
The chapter 3 questions.
Chapter 3, the homework? I don't have any on me, but I could get it later.
Oh, no, you're good.
Are we gonna quickly have 2 packets of these?
Yeah, because usually I give out the lab and then the homework.
Okay, cool, thank you.
Bees, and I got this thing to test them for mites. And there's 3 ways you could do it. One was an alcohol wash, one was a powdered sugar wash, and then one was CO2. The alcohol kills them all because you have to do like 300 bees. And the powdered sugar doesn't kill them all at all, but it does say that CO2 kind of did. do you think the CO2 route would be a good way to go with
So you're
them?
trying to kill them, or?
Well, you gotta check them for mites, I guess. So they got CO2 cartridges that you put in this container and you shake it to see if any come off. But I'm like, CO2 kind of sounds like it would kill more than just like a couple of them. So I don't know if that would
Yeah.
be kind of the route to go.
Yeah, I'm not sure.
I know, I'm like, because you gotta put them in like a locked container. But I'm like, I don't want to murder 300 bees
Yeah,
just to
'cause-
test them for mites. I think they would die that way.
yeah,
For CO2.
yeah, because the CO2 will suffocate them.
That's what I thought. I was like,
Yeah, it's kind of interesting testing methods. But
I know. Well, they said alcohol, which you have to shake them in isopropyl, and that'll definitely kill them
yeah,
all. And it did say, like, with the CO2, some would survive, but it's like, I don't want to, my hive's pretty small, and I don't want to
Yeah.
murder them, so I don't think the CO2 route is going to be the
yeah,
best
huh, that's kind of weird.
course of action, so I'll probably just do the powdered sugar. I know, that's what I was thinking. Because you said that it,
Yeah, because I mean, I just suffocate them. So.
thank you.
All right, let's go ahead and get started. And so I just want to we'll finish up a little bit on chapter 3 with the electron configuration. And I do apologize, I guess there's probably like a cold going around, so I seem to have been infected by it. But, you know, I tested negative for COVID, so there's that, still here. But I apologize. All right, so let's kind of continue. So where were we? Of course, now I try to find my periodic table. Sorry. So we were filling up our electron configuration, and so let's finish it up. So we were on the 4p over here with gallium. And so rubidium 5s, that's pretty self-explanatory. Going through. So right, this is 4d now with yttrium. And then back to 5p with indium. So 6s is cesium. And then this is where things get weird. And so now we need to start the F block. And so let's kind of at least talk about F orbitals briefly. So F orbitals. So sometimes I will get inspired and draw pictures of d orbitals, but I don't ever draw the F orbitals because they look crazy. So let's look at them. And so there are 7 of them. That's what we need to take away. So this is what they look like. So at least appreciate the picture, but we're never going to draw them. So there are 7 of them. So 1, 2, 3, 4, 5, 6, 7. And so with that, again, they can each hold 2 electrons in each one of these suborbitals. And so how many electrons is that total in the F? So 14. And so this is where the weirdness comes in. So it depends on your periodic table that you're looking at. And so what happens if we count this across? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's a little awkward. And so how I would do it and how it's usually filled up is we put lanthanide right here. So it's the start of 5D. So lanthanum is 5D. So we're at 57. And then we go cerium now starts 4F. And so it's like we're inserting that whole thing there. And again, you will see discrepancies on periodic tables. So sometimes I've seen lutetium and lawrencium thrown here, like they're the start of 5D and 6D. So I wouldn't put that personally. It doesn't match either what we find on our P table. But that's where, again, discrepancies might arise in different answers that you see. And so let's fill up the rest of the periodic table, and then we'll do some examples And it's a practice, and then go back to a question that was asked about what about the transition metals, and how do we do that? All right, so then, right, we're at cerium. So then this takes us down to 4F14 at lutetium, so we're at 71. Then 72, right, we're back at 5D2 here with hafnium. So does that make sense? So we could practice hafnium, but basically, starting at xenon, we have to do the 6S, then the 4F, and back to 5D. The thallium brings us back to 6P, and then I'll just finish it out. So 7S, right, actinium is 6D, thorium is 5F. So then this brings us back to 6D2 on element 104, and then getting to these weird synthetic elements. So, right, that would be 7P. So let's go back, and let's just start with some transition metal ones. And so let's look at chromium. So see if you can write the electron configuration for chromium, and then we'll look at it. All right, we ready for chromium? So what did people get? So argon, and then where do we go from there?
I got 4S2.
4S2.
And then
3D4. And so this is totally acceptable, right? So this is just filling it up what we expect. So starting at argon, so 4P2, 3D1, 2, 3, 4. So that looks good. But then, and this goes kind of back to the question I think that was asked last Thursday, why is it, so now we're checking it on P table. And so what do you notice about the P table answer?
It takes the electron out of 4S and puts it in 4D or 5D.
Yeah, the
Or
3D.
fifth slot of 3D.
Exactly. And so on an exam, because I don't want to drive people crazy, right, this would be an okay answer, right? So this is totally acceptable. But then what we want to understand, and what I might ask on an exam is, well, why is it actually this? And so let's talk about that. So we find that it's actually so 4S1, 3D5. And so if we look at that, so let's look at the P table. And we'll kind of talk about this as we go into our quantum mechanics chapter. But part of this principle is, so the energy gap is the largest between the lowest energy levels, so 1 and 2. But then each subsequent energy level, they get closer and closer and closer. So then when people say, well, why is there weird behavior? Well, this is a good hint. And so write what we expect, so we can draw 4s orbital here, and then our 3d. So again, what we kind of expect. But, right, we had to pay a price for pairing. So this is an energy price to pair. And so favorably, again, because the energy gap is so low, it must be more favorable to actually throw that extra electron in that D so that you don't have any pairing. And so I'll just rewrite that. So again, this is more energetically favorable. And so we'll kind of keep dancing around this. So I think later on, third quarter, we'll revisit kind of a crystal field theory. And again, that gives us just a brief look as to why the transition metals do what I say cool stuff, have cool colors. They also have a lot of transitions in what's called the visible region. So organic molecules, by contrast, have transitions in the UV region. And so we'll later learn, and again, how I've drawn these, just to reemphasize, is degenerate. But then why the d orbitals can do weird stuff is they can do all sorts of different configurations, like this or other things, depending on their geometry. And so this is like crystal field theory, which we'll put aside for later. All right, so we want to take away, at least we know how to do the acceptable method, but then start to get an understanding where we might see exceptions. And so that's something that you can play with, at home. So you can see, right, manganese fills up normally. And then if we go to copper, that's where we have some weirdness again. And so again, see similar patterns, niobium. And so this is kind of based off of its reactivity as well, kind of giving you a little hint.
Why would niobium do that if it doesn't even fill the 4D shell?
I'm not sure. This is probably indicative that it likes to be in a 5+ oxidation state, just based off of how it tends to react. But all right, now let's try a trickier one where we have to look at our kind of weirdness. And so let's try osmium here. So see if you can do the electron configuration for osmium. Don't forget, right, your 4F in there that gets inserted. Do we have an answer for osmium?
Xenon for my starting noble gas. And then 6s2, 4f14, and 5d5.
Is that what everybody got? Five D.
Oh, you're right, I forgot.
Oh.
I went in.
Yeah, so 1, 2, 3, 4, 5, 6. And so, right, you can always double check yourself. And so this is a good time to do a little check. And so, right, this is neutral osmium. And so we start with xenon. So 54, and then adding our little superscript. So 2 plus 14 plus 6. So that's 76, and then we can double check. Sorry, lots of scrolling. Back up to osmium. From 1, 2, 3, 4, 5, 6. And then just adding it helps us kind of double check that we didn't miscount, because, I mean, apparently a lot of people made that mistake, so easy to miscount. Let's do one more. Let's try 94, plutonium. See if we can write that electron configuration. Do we have an answer for plutonium, or are we still need more time? Oh, hang on. Let me scroll down. All right, what do we get?
I may have got the order incorrect, I was confused on that, but I got brackets with radon to start.
Okay.
7s2,
2,
5f5, and 61.
5F5, 61. So let's just double check the math here. So 86 plus 8 there. So 94, so that looks good. And then, so this is again one of those weird ones. So this is perfectly fine. This is what we expect. But then if you look at the P table, they actually say something different. So they have 7s2, 5f6, but again, right, we wouldn't know that without any other information. So just, again, be aware of discrepancies, and you will find different discrepancies. Yeah.
So like you were saying with the order, would the 60 come after the 5F?
So it doesn't matter too much as long as they're all there. I'd probably put the 60 before the 5F, just putting it in order, but like we saw, right, it doesn't even have it in the 61 officially, so, yeah. But yeah, I won't mark off points for putting it in different orders, that's fine. And if you had put the actual answer, again, that would also be fine, but I wouldn't expect you to know anybody. No. So official answer. I'll just put, right, we would need some sort of data. All right, do we feel okay on electron configuration? So it'll keep coming up as we talk about orbitals and all that. All right, so let's start chapter 4, although we will still talk about electron configuration with this first topic. And so we want to start with our ionization energy. And so let's define, well, what is ionization energy? So it's abbreviated IE. And so it's just defined as the minimum energy needed to remove an electron in the gas phase. So usually when they do these calculations, it's always in the gas phase. And so it always requires energy. So it's considered endothermic. So again, requires external energy. And of course, the valence electron is the easiest to remove, so it has the lowest ionization energy. And so then you just can write the symbol for each ionization. So we have here written the first ionization energy. So just our generic metal plus our ionization energy gives us metal cation plus electron. And so let's put at least some context to it. So we could say, right, sodium in the gas form plus its ionization energy gives us a sodium cation plus that electron. So this is like half of the process, right, to make sodium chloride. So half of it formally and energetically is, again, removing the electron with this ionization energy. And now we can write each subsequent energy. So now with the second ionization energy, you start with your cation, right, with the 1 plus cation, and then remove your second electron. And so formally, right, we could be looking at magnesium plus in the gas state, and then do our second ionization to create our standard magnesium 2 plus. And again, it's always 1 electron. So each step, right, you're just getting 1 electron. And then we could continue in theory, so magnesium, right, 2 plus now our third ionization energy would give us magnesium 3 plus again 1 electron, etc., right? So you can keep going. All right, now we want to look at some trends. And so this is our trend. So this is a graph for our first ionization energies. So we have, right, hydrogen, helium, then lithium, right, beryllium, aluminum. So we have this pattern here. Notice, right, the transition metals get weird. We expect that. And then here's our, again, more transition metals. So the trend is not as defined, again, from those D. But what causes this, like, spike here? What do you notice? What can we say? Yeah.
The noble gases have a really high first ionization energy.
And so why is that?
Because they're stable, they have full orbitals, so they don't really want to do anything.
Yeah, exactly. So now we can think back to the electron configuration. So, okay, we're already seeing some things. So we have helium even, which we said, right, was the duet rule, but even that is pretty satisfied. And of course, neon, right, 1s2, 2s2, 2p6. So we're seeing that how the electron configuration is reflected there. That's good. What about the lowest ones? What do we notice? So those are all the alkali metals. Excellent. So write our NS1 ending. So we're alkali metals.
So they all have an unfilled orbital, so they want to get rid of one electron, or two, depending on which row you're in, which column.
Yeah, so lithium, right, they want to get rid of one. Magnesium, two. So there's, right, slightly increasing energy, though, as we go across. Then why is there a drop here? So, right, we go lithium, beryllium, aluminum. Why is that? What does the electron configuration tell us? So then what electron are you ejecting, basically, from the aluminum? Why is it probably less energy than,
That's a little few.
Yeah, because it's one electron.
or not aluminum, sorry, boron. My bad.
It's one electron in the 2p.
Yeah, exactly. And so let's rewrite that, sorry. So we have, I'll write the electron configuration. So 1s2, 2s2, 2p1. And let's compare that to, so I was looking at, and I'm sorry for saying that was aluminum. So comparing boron and beryllium. So beryllium, 1s2, 2s2. And so exactly, I think everybody spotted it. So we have just one electron in that p. And so let's actually redraw that. So boron, we have our 2p, so our 2s here, versus beryllium. So it just has those in the 2s. And so for boron, yes, it is lower in energy since it's just ejecting one electron from that p, but then beryllium is slightly higher, right, since we have to unpair these electrons. So slightly higher to eject that paired electron there versus just ejecting one in the p. So does that make sense for that one?
And that's repeated with every row.
Yep, so then, now this is actually aluminum. So sodium, magnesium, aluminum, so that gets repeated again. So with, again, just one in the p. You also have a slight dip. So notice, let's go back to this one. So boron, carbon, nitrogen, oxygen. So again, you have a slight dip. So let's compare nitrogen versus oxygen. So right, nitrogen, so we have our 2p. So of course our S is filled. It has an electron in each p. We could draw, right, our Lewis dot structure while we're at it versus oxygen. And so right, nitrogen, we have to eject this electron from the happy p orbital where they have one electron in each p. So it doesn't want to do that. So that takes a little bit more energy. Versus oxygen, right? These electrons don't really want to be paired, so it's a little less energy to eject that then. So yeah, you see that slight dip for oxygen, and then back up, of course, to fluorine.
Atoms like having a half-filled orbital.
Yeah,
Like
they,
if you had like a 4f7, like that would be, they would be happy like that because each orbital has one electron.
ideally, yeah. So 4f7 with one in each one could be a good configuration, yeah.
Okay.
And so that gives us that slight dip there. But again, we can just say, so let's just write our general trend at least. So in general, right, ionization energy increases as we go across the periodic table, right, as you tend to fill up your orbitals and it gets closer to the octet. It usually takes more and more energy. And then down the periodic table, right, ionization energy decreases. And so if we go back to our chart, right, we see that. So let's just look at like lithium, sodium, potassium, rubidium, right? They all get a little lower in energy. So same thing with our noble gases as we go across, right? All kind of lower in energy as you go down, right? And then that electron is further out from the nucleus. And so again, we see that trend repeated. So aluminum, silicon, phosphorus, right? Then sulfur, and then chlorine, argon. And again, a lack of trend in our transition metal elements. And so ionization energy. And so now this is also explaining what's going on. So we've kind of stated it, but the word that they're going to use is effective nuclear charge. So of course, right, the larger the nuclear charge, the more energy it takes to remove it. And so that's just comparing, right, your charge. So of course you have your positive charge in the center from your protons, and then how far out is it or close, right? So of course if your electron is closer to the nucleus, then it's going to take more energy. And of course we saw those trends with the P and the S. So this is just another chart so we can see, right, ionization energy increases as we go from left to right and then decreases as we add more shells. Okay, blah, blah, blah. And so what's interesting is then we want to look at the second and also successive ionization energies. And so what we want to get from this is kind of where is the jump. And well, what do I mean by that? And so let's compare. So we're looking at this graph, right, of each subsequent ionization energy. So it has up to the first three for these. And so, right, we have, so looking at sodium, let me move down a little bit. So sodium, right, our first ionization energy is relatively low. And then all of a sudden, right, the second ionization energy is a lot higher. So what accounts for that?
Could be because it has a full 2p orbital, and it doesn't want to give up that full orbital. Because it has the same number of electrons as neon at that point.
Excellent. So let's write that. So, right, we notice our jump there. So this is also telling us, like, how many valence electrons sodium has. And then you're recognizing, yes, now it's like neon, so it's going to have this huge jump. And so I'm just going to rewrite the electron configuration for a second. So we're at neon, 3s1. So right then we remove it. So with our first ionization energy, so right first ionization energy, so sodium plus our first ionization energy gives us sodium plus. And so right, sodium plus is then neon. And so yes, with that gap, just like y'all notice, now we're trying to kick out our core electrons, so of course, that's why there's such a large increase in energy. And then magnesium, so what do you notice about magnesium and where that jump is?
The first two electrons you take away are pretty easy. once it gets to neon again, it doesn't want to give away its full 3p orbital. No, 2p orbital.
Yeah. So excellent. So that was good. So again, notice, right, the first ionization is always the smallest. So then we have the second one, but right, still relatively close together. And then yes, huge gap for that third, just like you noticed, right, as soon as we go back to the neon configuration, now it is a lot higher energy.
That's because you're trying to remove core electrons.
Yeah, so now we're trying to remove the core, so that would be not favorable, exactly.
What do you mean by core electrons?
So then core are just more of the inside,
Okay.
yeah.
Anything that's not shell.
Is it, are people in 211 by any chance? Biology 211?
Yeah, I already took it.
Okay. I know at least a few people are in it now. So not a lot of people are in it.
Not right now. Not this term.
I know one person is. Well, yeah. I'll reserve my tangent then, if not too many people are involved. All right, so then what we find, and so this is a nice graph, but basically this staircase highlights the jump, and then you can see, right, each jump then corresponds to how many valence electrons it has. So like we saw with sodium, the jump is between 1 and 2. So of course sodium has 1 valence electron. Magnesium, the jump is from 2 to 3, so of course that corresponds to 2 valence electrons. Aluminum, right, 4, so that corresponds to 3 valence electrons, and etc. So again, you can see that trend. So what you might expect on an exam is I would probably not have like the elements listed there, and then you would just have these numbers like 578, 1820, 2750, and then 11,600, and then based off of that data, you try to determine then how many valence electrons. So then looking at that data, right, you look for the gap and then say, okay, it probably has 3 valence electrons. So then it might be, right, aluminum, gallium, or boron based off of, again, that data. Does that make sense? All right, so we have these Lewis dot figures here. We've kind of talked about them. We should at least mention this exception. So they wrote carbon like this, but this is fine for the other group 4 analogs. So, right, silicon, that's fine if silicon is like that, germanium. So I think I might have mentioned that in this class. But for carbon, it's generally accepted that it always hybridizes, so this is a better structure. I'm surprised your book had that. But yeah, this is good. I like this for magnesium. I just want to point out, so how your textbook has it, I like it. This is reflective, right, of our electron configuration, that it's 3s2, so we want to put 2 electrons on one side. So I've seen textbooks before where they write magnesium like this, and I don't really like that just because it's not, it doesn't translate back to the electron configuration. Any questions on Lewis dot structures before we just kind of skip over it?
I actually have a question. So when you're drawing out, like, say, sodium and chlorine are like reacting with the Lewis dot structure, you can only have a line where if it was by itself there would be a dot. Is that correct? Is that a question that makes sense?
Sorry, I actually don't get what you're asking, but
So like I can write up my question on the board if you want so everyone can see what I'm
yeah,
saying.
I mean, I'm just thinking,
Imagining.
right, you have sodium plus chlorine, And then eventually, right, they'll make sodium plus chloride. But
You can write it like with a line between the two, so Na would bind with chlorine, right? And then you could draw the remaining
That's
dots around
maybe like a
chlorine.
covalent bond.
oh, you're talking about like this?
Yeah, but then you would draw the remaining dots around chlorine.
Yeah, you wouldn't do that because this shows like a bond. Yeah. So this shows a covalent bond, but that would be right not correct for an ionic compound. So I would not draw that.
Okay, but it would work for, I don't know, nitrogen and you know, something else.
Yeah.
Or like carbon dioxide.
Yeah, carbon
That
dioxide,
one's an
right?
easy one.
That works because that's showing that yes, those are covalent bonds. And, you know, later we'll get into like, yes, these are double bonds and all that sort of thing. But when you're writing like an ionic compound, you don't want to draw a line between them. And so let's just do like even, so like magnesium sulfate, right? So sulfate, and we haven't quite gotten there, right? But this is a polyatomic ion. And so we can draw this, right, covalently. So negative charge. And then we just want to draw, right, magnesium kind of hanging out with it. So no bonds between them because it's just an electrostatic interaction. Sometimes what I've seen before in like papers, this would be more with like crown ethers. And I probably can't draw a crown ether. Plus there's all sorts of crown ethers. But basically, let's say you have like sodium and usually crown ethers. Oh my gosh. They're like some sort of oxygen repeating compound. I probably screwed this up. So it looks something like that. So it depends on how big your crown ether is. They all are different sizes. But sometimes papers kind of draw this weird like dotted lines to kind of show that it's in the middle, but it would still be right electrostatic interaction. So no true covalent bond there.
Gotcha, okay.
Other questions on Lewis dots? So, and then, right, we're clear, maybe we should do, right, we're clear that it like repeats a pattern. So group 1, right, they all have 1 dot. It doesn't matter what side, right? Group 2, they all have 2 dots, right? Magnesium, whatever, calcium. So they all repeat patterns. So does everybody see that? I don't want to go too fast, but also don't want to bore people. So you gotta let me know how you're feeling. Right, so group 5, we could say, right, they like to make 3 bonds here because they have those 3 little electrons there. We see that. So group 6, they always tend to make 2 bonds. And group 7, of course, makes 1 in general.
All the elements in those groups too have the same amount of valence electrons, right?
Yeah, so right, you could swap this with sulfur, selenium, yeah, chlorine, bromine, iodine for that one. All right, any other questions about electron configuration or ionization energy before we start going more into quantum mechanics? So it kind of feels like we take a detour, and I guess this is also one of those like philosophical teaching questions for chemistry instructors is like, where do you put quantum mechanics? And so don't let quantum mechanics scare you if you're not a fan. And either people like really like it because it's math and formulas, or people don't like it and it doesn't feel as chemistry-ish. But to at least appreciate all these pictures that I'm talking about with orbitals and like how we got there, we have to take a step backwards and kind of understand the history at least and quantum mechanics, so where things came from. And so a lot of this work was done, fairly recently. So in the early 20th century, they began kind of exploring the quantum matter. And so there were a lot of really smart people at the time all kind of working together and talking, collaborating. So of course, Einstein, and then Bohr, de Broglie, Max Planck, Heisenberg, Dirac, and Schrödinger, So they're all writing these equations as well to try to understand quantum mechanics. And so a lot of this work laid the foundation of like our modern computational chemistry. And so I think like second quarter we'll play with some computations, but I'll probably show you some at some point and I'll get overexcited, right? But then that kind of gives us these pretty pictures and the MO diagrams, and now we're really understanding kind of what's going on and how are things reacting. And of course, the other thing that they started noticing is that really small things started behaving differently than macroscopic. And so that was, of course, a difficult thing to kind of understand. And so, of course, at this time, there was also kind of this whole wave-particle duality that they were trying to understand. So, is a photon a particle? Is it a wave? And so they didn't really know. Of course, right now we have this wave-particle duality concept where we know photons behave both as a particle and as a wave. But of course, this created a lot of confusion when they were trying to study it. And so let's look at kind of the difficulty. And so it starts off with, of course, electrons are incredibly small. And so, they give this analogy. So the number of electrons in a single speck of dust is higher than the number of people who've ever lived on Earth. And so, of course, trying to observe then this electron is pretty difficult, if not impossible. And so, the issue is as soon as you try to observe it, measure it, now you're perturbing its behavior. And so, it mentions, so even if you're trying to shine just a light at the electron, right now you've already messed up the behavior. And so that was, again, difficult. And of course, much of the atom's behavior is determined by the electron. And so our quantum mechanical model, it tells us the light wave nature and does not explain the particulate matter of the electron. Again, we can simplify it as a wave. And so the electron cannot be viewed as just a small piece of matter around the nucleus, but as a cloud of probable positions. So this is kind of the key point, So mathematically, we're really just determining where is it going to be. And so what else does quantum mechanics tell us? And so, we've kind of touched on it, but we're just continuing to dive into more about, the periodic tables, its trends. So we'll look into, why oxygen is paramagnetic later on. So probably tease that too early. But also chemical bonding. It's really powerful Because again, we're going to use computational chemistry to kind of verify our results, but we can do a lot of what I would call back of the envelope calculations, and you can get pretty accurate picture of what's going on with bonding, right? How many electrons do you have? How many unpaired or paired electrons? And so with that comes like colors and all that, how that relates. And so this is also kind of tying back into why things are metals and non-metals. So we're seeing that with our trends. Again, we're already kind of getting there, but quantum mechanics just helps solidify that. So now let's look at light and its wave nature. So light is just a form of electromagnetic radiation. And so anything that's defined as electromagnetic radiation has perpendicular oscillating waves, one for your electric field and one for the magnetic field. And so key is all electromagnetic waves move through space at the same speed. So I would star this, so 3 times 10 to the 8th meters per second. So that's the speed of light there. And so, right, this is just what your electromagnetic wave looks like. So here's your wave component and then direction of travel.
Sorry, what was the speed of light estimate there again? 3 times 10 was 6?
8. Yeah. So you might want to write this down, especially as we go into this chapter, because you'll use this a lot with our calculations. And so now let's look at how we characterize a wave. So we have what's called our amplitude. So this is our height of the wave. And so notice, right, it's just from the origin to the height, or you could also measure amplitude right from the lowest point. Then we have the wavelength. So this is really important. So it's either right crest to crest or trough to trough, and that gives us the wavelength. So using the symbol lambda. Oh, and going back to amplitude. So amplitude, this would correspond to light intensity. So the brighter your amplitude, the brighter the light, right? But that doesn't change your energy. So this is kind of important, and we'll rope back as to why. So again, wavelength, that's pretty key. So we'll talk about wavelengths, right? So these wavelengths also correspond to color. So we'll get there. And so this is important. So again, right, wavelength and amplitude are independent properties. And so it's the wavelength, right, that determines its color. So the wavelength determines the color. So maybe you've seen that with different lasers. So again, they're all different wavelengths, different colors here. So red, notice, has the long wavelength. So red tends to be lower energy versus blue, where it's shorter wavelength, so higher frequency. And then these two lights, right, it looks like they have the same wavelength, just kind of roughly judging, right? They're crest to crest there. But the only difference is in their amplitude, so this would be a dim light versus a bright light. And so again, the color is determined by its wavelength. So of course, white light is a mixture of all the colors of the light. And so next week in lab, I think we'll get to play with it. So there'll be a flame test, and you'll get a look at these spectrums. So you'll get to see that your fluorescent light is indeed the whole rainbow. And so hopefully, right, you know Roy G. Biv. So red, orange, yellow, green, blue, indigo, and violet. And again, we'll go over that red is the lowest energy, and violet is the highest energy. And so then we'll also look at, well, what gives us color. And so when an object absorbs some of the wavelengths of white light and reflects others, it appears colored. And so the observed color is predominantly, right, the color reflected. So if you're talking about like a green leaf, so let's think about a green leaf. So, right, a green leaf, obviously, right, it looks green to our eye. And maybe I should draw a little better picture. So, right, let's draw our leaf here. And so we could think about light. So, right, light is being absorbed. And then if green is getting reflected, what do you think the plant is absorbing then?
I'm just absorbing red.
Yeah. So, right, the plant is absorbing energy. And, right, the red spectrum. And then it doesn't absorb a lot of green, so then we see that green reflected. And so, like I said, we'll play around with that in lab and kind of looking at the color wheel. Yeah.
Wouldn't it be absorbing green since it's bouncing away?
But it's whatever one, so it absorbs the opposite of what you see. So if it looks green, that means it's absorbing red.
It'd be right red. It's slightly moving, it's absorbing everything from the so it's not just red. Blue,
So does that
yeah.
clarify? And so we'll also look at the frequency. So frequency is related to our energy. So frequency is this little like V symbol, so like a curly V or nu. And so frequency is just defined as the number of waves that pass the point in a given period of time. And so the unit, since it's over a period, it would be in hertz or inverse seconds here. And so then total energy is proportional to the amplitude of the waves and their frequency. So the larger the amplitude, again, the more force.
What was the hertz cycle again?
So this is just a frequency, but we'll do some calculations. So that's just the unit. So 1 hertz is just either per second or hertz. So that's like how many times like our crest passes a certain point.
Okay.
So we'll see that. And so now we're getting to the math. And so I would probably write this formula down because we'll use it a billion times in this chapter. And right, so we said, well, all electromagnetic waves, they all travel at c. So right, c is just the speed of light. So 3.0 times 10 to the 8 meters per second. So rewriting that. And so now what we're also seeing, and so let's think of, again, red versus purple. So red, it tends to have a longer wavelength versus purple. So purple is shorter wavelength, higher frequency. And so now we see, right, if we're measuring, so the waves are traveling, we want to measure how many times they hit this point here. Well, this one only hit, right, 2 times in a given time period versus this one hitting, right, 1, 2, 3, 4, 5, 6, 7, or whatever. I just made up some graphs here. But the key point is so if we have a longer wavelength, like with this red, we would have a lower frequency, right? So those long wavelengths, so obviously they're not going to be passing by this point as often. Versus the shorter wavelength, such as with purple, where it's going to have a lot higher frequency. And so again, right, that frequency is what gives it the energy. So you probably want to write this down with your frequency is, again, your speed of light divided by your wavelength then. And so you can do the units, right? So just doing our unit on it. So 3 times 10 to the 8th, so meters per second, divided by our meters. So, right, meters cancels to give you 1/seconds, which is hertz. So all that matches up there. All right, see if you can do this little practice here. So just calculate the wavelength in nanometers of red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14 hertz. So looking for answers. So do we have answers? So 649, is that what other people got? So I see some nods. So, right, we could set up our little triangle trick to help us. And so we want to solve for wavelength. So we need to take our speed divided by our frequency. So is that what everybody did? So then do we get this answer? And of course, right, this is in meters, though. So 6.49 times 10 to the negative 7 meters. And then if you did the conversion, then yeah, 649 nanometers. So you can just multiply this by 1 times 10 to the 9th here. Oops. Questions about this one? Questions? Not too bad then. And so now we want to look at the whole electromagnetic spectrum here. And so now we're looking at our electromagnetic spectrum. So right, we have frequency, so low frequency on our left side, high frequency on the right. And so right, low frequency, low energy, that's going to be your radio waves. And right, so this is why those AM waves travel really far, so they're really long, so they can go right across the country. And then FM waves, so they travel shorter. And we have kind of cell phone. And so, right, with that, so we could talk about 5G. So 5G, kind of the interesting thing about 5G is that it's a little bit higher energy, but then right, those 5G waves can't go as far, so that's why when they were prepping for 5G, right, they put a bunch of repeater boxes everywhere so those waves can be repeated. So that is a challenge with 5G. And we have microwave is around this area, so then we go from microwave to infrared. And so you can always remember, right, you have infrared, and that's right next to red. And so, right, you also want to appreciate, well, our visible region is pretty small compared to the rest, so of course we can't see all these other waves, so we only see our visible spectrum. And then at least appreciate the numbers. So again, they're in nanometers, so about 750 to 400. We'll see in lab, not this week, but next week when we play with our little spectrophotometers, we'll have little like 7, 6, 5, 4 that corresponds to that. And then now going into the higher energy, so of course we have UV, and right, UV can start to, of course, do damage, and then X-rays, right? So of course, X-rays, if you're in the medical field, right, you want to limit your exposure to them. And actually, like the guy that invented X-rays, he accidentally gave his wife cancer because he was like, you know, experimenting and taking too many pictures of her hand and stuff. So yeah, now, you know, they've dialed down the radiation back from when they were discovering it, but yeah, that's why it's important to, of course, keep yourself protected, limit exposure. And then all the way to gamma rays, which can be high energy and potentially destructive.
Is
Or
there any limit to the gamma ray? Or is there a cap? How high energy gamma rays can be?
I would have to look at like the literature to see, because gamma rays are also sometimes involved in like atomic bombs, but yeah, I'm not sure like how high they go frequency wise. And so again, right, we're just appreciating that we can only see a small fraction of our electromagnetic spectrum. And just comparing, again, shorter wavelength light has higher energy. And so again, radio waves have that low energy because they're very long and big, while gamma rays have the highest. And again, right, those UV rays, so of course, right, long-term sun exposure, but we mentioned X-rays and gamma rays can damage biological molecules, right, cause mutations in your DNA or damage bonds. And so again, next week in lab, we'll get to play with this. So kind of what happens now when atoms absorb energy. And so when atoms absorb energy, right, that energy has to then be released as light. And so we'll look at that. So when that emitted light is passed through a prism, a pattern of particular wavelengths of light is seen that is unique to that atom or molecule. And so this could be a way to identify molecules in space, is by looking at their emission spectrum, so then you can identify different elements and figure out what stars are made out of. And so we'll look at the emission spectrum for different elements. And so again, right, that line spectrum is used to identify elements since each one has its own unique spectrum, right? Kind of like your fingerprint. And so we'll look at hydrogen, and so how this works. And again, we'll look at this. But you have your hydrogen lamp, so of course you have hydrogen gas in here, and then you're passing electricity through. So that electricity, of course, then excites the electrons. And so we have a hydrogen, so one electron in the 1s, and then that can get promoted to subsequent higher energy levels. Then that gives us a pretty picture, which again you'll get to see next week. And so what you'll find, so again, why we focus on hydrogen is, of course, it's the simplest, and you can figure out where its lines might be from. So hydrogen has 4 distinct lines. I think you can see more. And so this is an example of what you'll see. So again, you have helium now. So of course, helium has 2 electrons, and you can see how that looks, right? And now barium, so barium is already looking more complicated. And then, right, this is just comparing it to your white light spectrum.
And these lines on the spectrum are just like where an electron is likely to be found?
Well,
Like,
they
is it
correspond,
orbital?
so they correspond to some transition. So we're not answering what transition right now, but right, and we'll look at some calculations, but right, let's say the electron goes from the 1s to the 2s, right? And then you're calculating, well, what is that energy gap there? And then what is the wavelength corresponding to that, essentially? But, right, you can imagine it gets pretty complicated pretty quickly, right? So then you have a lot of orbitals, you can have all these small transitions, and so that's why you have a lot of lines then. And so this is just the absorption spectrum, which is pretty similar. So you would get the same data, it's just basically the inverse where you have the full light spectrum and then you're seeing what's kind of being removed there. So again, same information, just looks a little different. So this would be indicating what's being absorbed and promoting. Yeah.
Can you use like look at the spectrum and see what the element would look like in like a solid film? Like that condense oxygen into a solid state? Would it look blue as most of the lines on the
Oxygen actually is blue when you condense it down, but I'm not sure that that's why that is, because these are reflective of more of the transitions, so like all the electrons being promoted in the excited state. So I'm not actually sure why oxygen is blue as a liquid. Other questions? And so now we want to kind of translate these to, well, what are we looking at? And so we go back to kind of, right, the Bohr model. So the nuclear model of the atom, so Rutherford, so what is Rutherford's model? So Rutherford so he had kind of, right, the oversimplified picture. So atom, and I think they at least established, right, some sort of proton in the center and some electron cloud around it. But the problem with this model, right, is it's not really explaining, well, why do we have this emission spectrum? What is going on when the atom gains or loses energy? So then we got to this Bohr model, which is kind of our next step. Still oversimplified, but we're going to look at this kind of oversimplified approach for these calculations. And so Bohr is basically the onion ring model. So now he's saying, well, we have these distinct transitions, right? And so that means that there has to be quantized energy or some sort of packets, so some sort of set transitions. And so it came into this model. And so again, right, energy of the atom was quantized. And so that means, right, we have to have a particular specific amount. And so because it's a specific amount, right, it has to probably correspond to some sort of transition. So looking at that, right, it could be the 2-to-1 transition, right, 3-to-1, 3-to-2, that sort of thing. But, right, it has to be some sort of quantized set energy level. It's going to be the same, right, every time. Because that's the other thing that we're seeing, right, from our hydrogen spectrum. It's not going to change. It's not going to be different, right? It's always the same. So why is that? So quantized just means like a specific amount. And so we'll do the calculation. But again, if we're thinking about the energy transition from like 2-to-1, right, that's always going to have the same energy difference. So there's some sort of, right, difference in energy that's related to that transition. And then that energy, right, gives us a pretty color, which we can see. But then, oh, okay, that's actually from, right, a transition. So the electron going down from a higher energy level to a lower one. And then you see that color given off. Does that answer quantized?
So it's not necessarily atoms, but like elements. So like all helium, like atoms have the same amount of like energy between them all. That's why the spectrum is always the same, no matter.
Right, but it's still
What
the electrons, right? So,
Yeah.
so it's the fact that helium has 2 electrons now, but then it's every like allowed transition. So, right, it could be the 1s to the 2s or the 2p. Well, it would really be the relaxation that you're seeing. So, right, 2p to the 1s, etc. So you go crazy, right? So go back to the p table or something. And so, right, we could predict every transition possible. So that would get like crazy, right? But so that's what we're getting.
What are you talking about? Are the electrons like swapping places with each other or something? Is that what the transitions are?
So they're not swapping places, but let's go back to this one. So what happens, right? So you have your hydrogen lamp, and then you're putting electrons through it, right? So that gives it energy. And so once you give it energy, right, that promotes, because this is just called our ground state here. So now let's relabel this, right? So this is our ground state electron configuration. But once you have energy now, it could be promoted to something else, right? So now let's just say it got promoted to the 2s1 now, an electron, and then we would be observing that transition as it relaxes back to the ground state. And then this transition corresponds to some sort of energy, which corresponds to a color. Does that make sense?
Okay, and it releases that color because it releases a specific amount of energy, which gives out a specific wave, which releases that in a form of a specific wavelength of light, which is why we see that
Yeah,
specific wavelength.
yeah,
Why we can see it through the, okay.
yeah.
So the electrons aren't necessarily confined to, like in helium, the normal shells that they're in. Like an electron can jump up, like you said, to 2s1, and then go back down to where it wants to be, which is in the 1s.
Right. So yeah, so this could be our ground state for helium, and then we could say, right, excited state helium, we could have 1s1, 2s1, or only one is promoted. You could have two promoted, right? So then you have all sorts of different transitions.
Okay.
It's now, right, excited state. And so with that, so at least, right, we're kind of seeing, well, it's a set transition, right? So it corresponds to a set energy level. And so that's where we got this kind of Bohr's model, where we said electrons travel in orbits that are fixed distance from the nucleus. So again, right, this is not quite true from our modern perspective, right? Again, we said that we've kind of moved to this probability density map with electrons. But again, we're looking at just kind of the oversimplification and our allowed transitions. And so, right, we're saying if they're at a fixed distance, then this is what we're looking at, right? The transition of higher energy states to lower. And so, right, that gives us, so then the energy of the electron is proportional to the distance that the orbit is from the nucleus. And again, right, they jump from a higher energy back down to the ground state. Oops. Yeah.
I'm just trying to like distinguish in my head. So like atoms like reflecting a color normally, that's different than what we're talking about right now, right? Like we're talking about when they get excited by like the influx of outside energy and then emit a color.
Yeah.
Okay.
And so we'll talk about sodium, because this might help, because we're talking about its color in its excited state. And so, right, thinking about sodium, well, sodium is, right, a metallic gray solid, but when you light it up, so you're going to light it up next week, right, it's a nice orange flame. And then if you were to take that orange flame and then look at the emission spectrum, so let's now see if we can find it. So sodium. Oh, come on. I was looking for a better picture. So we actually have like really nice pictures in lab so we have the periodic table of the emission spectrum in lab. So that'll be a much better sense to look at. But yes, so then, right, you burn it, it burns orange, and then that orange color would correspond to this emission spectrum that's related to, right, the electrons being excited and then jumping back down. So yeah, it's not related to this necessarily. So it's excited color, or, you know, again, back to the noble gases, you excite them with electrons passing through, and then you have, right, the neon lights because of that. And so this is a good picture because now we can start to see what's going on. And so we have here, so write this n equals 5 transition, so 5 back down to 2. So that corresponds to a higher energy. So that's, right, again, 5 to 2, so that's a larger transition. So we expect that to be a little higher in energy versus like a smaller transition from 3 to 2. So that would correspond with red. And so then we have, so we'll just, again, we're kind of taking an oversimplified approach with this, and we're mainly just going to be looking at hydrogen then. And so we're just looking at our principal quantum energy levels, again, just kind of oversimplified. And then energies are always defined as negative. So an electron's energy is lowered as a result of the interaction with the nucleus. And so this is a useful formula that we'll want. And so we have energy, and this is of each then principal level. Again, this is only for hydrogen here, but our energy corresponds to this formula. So if you like attajoules, now would be the time to use it. I usually just keep it in this 10 to the negative 18. So we have energy of each energy level. So write n equals 1, 2, 3, where n is just our principal quantum energy levels. But then you can figure out the energy at each level based off of this formula. Again, we're just appreciating the largest transition is from 2 to 1, and each subsequent one gets smaller and smaller and smaller. If you have n equals infinity, if you see this in a problem, this corresponds to your escape energy. That's right, if n equals infinity, then your electron has left the building.
In that equation, u subscript n was the energy that's released when it moves from a certain state back down to the ground, right?
So this is just the energy at a single energy level. We will be given another formula that lays out the transitions better. So yeah, this is just for like if you want to figure out for the 1 level or the 2. Oh, thought I had that formula. I guess not. So let's write that. Bag. Usually, so I'll write that since I didn't put that. But usually when you're trying to find the difference, right, you do negative 2.18 times 10 to negative 18 joules, and it's just 1 over n f squared minus 1 over n initial squared. So that gives you your difference then in energy. So that's probably in your book. And so now, well, how do we get there? How do we figure out that everything was quantized? And so this was pretty interesting. So this is a photoelectric effect, and this kind of goes back to why things are quantized. So they observed, so first of all, it started off with a red light. So started to shine a red light at a surface, nothing happened, right? You can increase the intensity of that red light, nothing happens. But then change it to a blue light, and now all of a sudden, electrons are emitted. So that was interesting. And so that was the photoelectric effect. But then the other kind of issue, and so this goes back to kind of that quantized issue and how they determine that the brightness has nothing to do with it, is from this photoelectric effect. So that was surprising, right? So they didn't quite understand how come if I shine the light with a high intensity, why doesn't it do anything? But it goes back to it has to be that perfect quantized packet that's appropriate to then, right, eject those electrons. So we can't just add energy, right? It doesn't build. It has to be the correct wavelength. So that was a good key experiment. And so let's look at what we expect. And so right from our kind of classical theory and thinking, so we expect that if we just change the light's intensity, right, more electrons should be ejected. That was not what happened, so let's write that, right, not what happened. So that was surprising. And so, right, it was only when we changed the wavelength. And so again, the thought was if the dim light was used, there should be some sort of lag time, but no, that was not the case. And so what does that tell us? So then, right, we tell us that there's some sort of minimum frequency was needed then. So, right, that goes back to corresponding to our Bohr model that it has to match up with a transition, right? We can't just shine the inappropriate light with the wrong wavelength, right? It's not going to work. So that's where we get this threshold frequency. And I'll just add, right, must be correct wavelength with that. And so even a dim source, right, as long as it was the correct frequency, so the high enough frequency of appropriate energy, right, that caused electron emission without any lag time. So that was interesting as well, right? So you could use a dim source. It didn't matter. It's all about the wavelength of the light. And so now we get, so we've kind of been dancing around this photons. And so now we get to the fact that light was then considered to be in little packets called photons. And so, right, it's like a little packet of energy kind of as a wavelength. And so energy can be defined as Planck's constant times our frequency. And so Planck's constant is down here. So Planck's constant is 6.626 times 10 to the negative 34 joule seconds. And so, right, you might see this form of the equation, but I just rewrote it. So, of course, you can substitute frequency equals speed of light over wavelength to give you this. So now we can see, right, how we can relate our energy of our transitions back to our wavelength. So this is exciting. So we had, right, energy is equal to this. And then if we add it with this formula, so now we can relate, right, our transitions to a wavelength. And so at this time, de Broglie was also, of course, in correspondence. And so everybody's kind of dancing around the same conclusions. So particles have this wave-like character. Sorry. And so de Broglie predicted that the wavelength of a particle was inversely proportional to its momentum. And so, right, this is only significant for electrons. And so let's do a little practice here. So let's figure out our de Broglie wavelength. And so now let's go. And so let's see, I'm pretty sure mass here needs to be in kilograms. And we have Planck's constant here. So 6.626 times 10 to the negative 34. And then this can be our speed. So right, V is speed. So let's first calculate our de Broglie wavelength. So let's say we're a 70 kilogram person moving at 1 meter per second. So what's my de Broglie wavelength? And then let's compare that to an electron, except I'll have to get the mass of the electron. So go ahead, at least start on that.
Are we just assuming that the electron is still at 1 meters per second?
Oh. So for this one, let's just plug in, let's do like 5.6 times 10 to the 6 meters per second. Because they usually don't move quite the speed of light, so usually a little under. So let's start with the person. So we just have to plug everything in. So 6.626 times 10 to the negative 34 mass in kilograms, just assuming 1. So what do we get for our de Broglie wavelength? Yeah, what do we get?
About 9.466 to the 10 negative 33.
What'd you get for the,
Negative 33.
oh, negative 33? Yeah, I got negative 36 as well. But basically, right, pretty tiny. So 9.46 times 10 to the negative 36 meters. So right, not too significant for us. So we're pretty large. So we're not on a scale of, right, negative 36 meters. But what happens with the electron? And like I said, if you plugged in the speed of light, that's also fine. That gives us a close enough approximation. But what do we get when we plug this in? So answers.
With your number for the speed of light, well, close to the speed of light, I got 40,073.51.
So died. Here, I'm still plugging it in. Times 5.6. Sounds a little high. But I get this when I do it. Do we get other things like this? So it's supposed to be at least somewhere on like the nanometer order. So right, I'll convert it to nanometers. So this is like kind of small, but like 0.13 nanometers roughly. But what we want to take away is, so right, this one is super tiny compared to our size. So that's why we don't really care about our de Broglie wavelength. That's why it doesn't matter for us. But once we start talking about things the size of an electron, right, the de Broglie wavelength does matter. So it is significant. So that's where we start to see some of that quantum behavior there. So if it's right on, if your de Broglie wavelength is on the nanometer scale and you're on the nanometer scale, right, that's why you have those properties exist. All right. We kind of flew through that chapter, which is surprising. All right, I think we'll end here, just in the interest of time. So probably Thursday we'll do some more practice on this, so we'll go through more calculations so we feel good.
Yes, please.
And then, so I will say, so if you have lab today, so I'm going to be dashing out because, so I have to help my husband get to a doctor's appointment. But the lab today, there's no chemicals, so you could do it at home. Dusty's going to be taking over my lab though. But if you could show up maybe like a little bit early, so like 1:20-ish, just so I could get y'all going, that'll be good. So that's only if you have lab today. Everything should be normal on Thursday. And so I apologize because I'm sick. I kind of fell behind on grading already, so I'm like in the middle of grading your quizzes, but I'll get those finished ASAP. And then you could turn stuff in to the front there.
So I can show up there for a little bit and go home. Just technically.
Well, you could do it the lab like in there, and so there are like cards that you will want to use. But yeah, if you wanted to go home, you totally could.
Okay.
But yeah.
I'll probably show up for a little bit and see what it's like.
Cool.